Okay, coming back for her second time here on stage is Kaixi Yang again to present DIP ECOD, improving anomaly detection and multimodal distributions.
So, hello again. So, CAMLIS is too good, so I'm able to present twice. So, hello again. My name is Kaixi Yang, or you can call me Kaixi if you like. I'm a PhD student in Queen's University Belfast in the UK. So today I'm going to talk about one of my projects, which is called DIP ECOD, which is the improving anomaly detection method, especially with focus on the multimodal distribution. So this is the topic I'm going to cover in my presentation today. And before I start the technical part, I would like to give you a quick introduction about the background of my project. So I guess some of you guys here work as an engineer before. So you know how the engineers work together. So let's see the graph on the right-hand side. When the engineers, they would like to make changes around the code, what do? They clone the GitHub repositories to their local machine and then create a branch. And then they start to make the changes, which is called commit. And then they create pull requests, wait for the approvals. Once the quality has been checked, and then the changes can be merged to the master branch. So that's how it works. However, you can see there's a problem. First, the number of the commit will be made is more than one, and also you will have more than one engineers in one team. So which means you could face like 1,000 or millions of commits to be reviewed by the team. So which is a large amount of data. And also the code has been changed, could introduce the risk, including the vulnerabilities and weaknesses. So it's necessary to have an early indicator which can detect those unusual commits at the early stage. For example, the commit stage, instead of we leave it until the development stage. And probably like most of you guys already know, one of the changes we face is we have a large amount of data set which is not labeled. And if we would like to label this data, it's very time consuming. And also some type of the data, we need the expert to label. So this challenge also applied in our project. We have a large amount of GitHub repositories, which is not labeled. So there are some current existing research which targets those problems. However, there are some limitations. First, some of them suffer from the curse of dimensionality. So which means when the features of the data is too high, the performance of the model reduce. And also some of the model require fine-tune the hyperparameters, which means it could be time consuming. And also some of the model is based on the assumption that the data set is unimodal distribution. So which means when the data set is multimodal distribution, the performance starts to drop. So let me give you a quick introduction about what is unimodal and what is multimodal data set, because this is the main focus in our project. So as you can see here, unimodal data has only one peak. And multimodal data set, including bimodal, has more than one peak. And if I give you an example about just to understand the multimodal data set better. So for example, let's say we have engineer in a company, and you would like to analyze the working pattern of this engineer. So say the engineer work from 9 a.m. to 5 p.m., and there's a lunch break around 12. So let's say if we analyze the number of the commit has been pushed to the GitHub commit, we would expect there is a peak around, let's say, 10 and 11 a.m. and then start to drop because drop around 12 because that's the time the engineer goes for have a lunch, and then it will start to go up again around 2 and 3 p.m. because that's the engineer start to work again, and then drop again around 5 p.m. And that's the engineer finish work. So I hope this example helps you to understand what is multimodal data set. So there is one anomaly detection method which I would like to emphasize here, which is called ECOD. So ECOD was published on TKDE journal in 2022, which achieved the best performance among all the anomaly detection methods. And the ECOD is an unsupervised learning anomaly detection method, which based on the empirical cumulative distribution function. So the intuition behind the ECOD is, let's say when we have a data set, which is a unimodal distribution on the graph shown here, and the outliers, we see, let's say the rare event usually lie at the tail of the distribution, as you can see here, as the green area show here. So we see the tail of the distribution, which means the two sides of the distribution. As you can see here, there's a problem. When we have assumption, the data set is unimodal distribution, the model performs very well. However, when we have a data set like multimodal distribution, the problems comes. ECOD can only identify the outliers lying at the tail, as the green area show here. However, it cannot detect outliers between the modes at the red circle here. So that brings the aim of our project. So we would like to develop this improving anomaly detection method, which can detect unusual behaviors from not only the unimodal distribution and also the multimodal distribution. How we're going to do it? This is our solution. We propose this novel method, which is called deep ECOD, by splitting the multimodal distribution into the unimodal distribution. And then we apply ECOD. So just to recall, the problem our model tried to solve here is to not only locate the outliers at the tail of the distribution and also the outliers lying between the modes. So let me go through the architecture of our proposed method called deep ECOD. Imagine if we have a data set. First thing, what we would like to do is to identify the modality of the data set by calculating the p-value. So say if we have data set which has unimodal distribution, we apply ECOD straight away. If the data set is multimodal distribution, we go to the second step, which is to estimate the model interval. How we're going to do it is to obtain the GCM and LCM. Here, GCM represents the greatest concave minority, and LCM represents least convex majority. And then after we got the model intervals, we go to the third step to split the component. How are we going to find the split point? So it's very simple. We would like to, so the split point is actually the middle point between the model intervals. And then we can split the multimodal distribution into the individual unimodal. And then we apply ECOD to calculate the outlier scores to identify the outliers. So let me give you a quick example to help you understand our model better. So first, let's say we have a data set which has bimodal or multimodal distribution. Now, what we're going to do is we will find the model intervals lying in those two areas. And then we find the split point, which is the middle point between the model intervals, which is 5. And then we split the multimodal into two individual unimodals. which is the first one lie between -3 and 5, and the second one lie between 5 and 13. And then we apply ECOD. So as you can see here, previously, ECOD can only identify the outliers at the tail of the distribution. And our improving method, the deep ECOD, can not only identify the outliers at the tail of the distribution and also between the modes. So I think you guys had enough of the technical part. So I think let's talk about something more interesting, which is the experiment part. So we pick those 9 public anomaly detection benchmark data set across in different fields, say satellite, wine, speech, diabetes. And we did the comparison with 8 other state-of-art anomaly detection methods. As you can see here, our proposed method, the deep ECOD, achieved the best result, which is 0.791 AUC score. Especially, we outperformed the second best ECOD with 0.761. And if we look into the result here, deep ECOD outperformed ECOD on all the multimodal data set, and we achieve the same performance on all the unimodal data set. And also, our project is sponsored by a large American company, so which means we are allowed to evaluate our data set, model on the real world data. So the real world data set we pick is about the GitHub repositories, and we pick this 10 GitHub repositories to evaluate our model. So our main focus is the commit from those repositories. So if you're wondering what the commit looks like, you can see here. So the line in red, which means the content has been deleted, and the line in green, which means the content has been added. So that's what the commit looks like. And the features we picked from the commit, including those 4 features, say what time and the date the commit has been made, and also the number of the line has been changed, and the number of deletion, number of addition, and the number of the commit from those 10 repositories varies from 100 to 300,000. So I will just pick one of the repository out of 10 repositories to demonstrate the result on the real world data set. So the repository we pick including 738 commits, and we set the contamination to 1%. So which means the 1%, the commit with highest outlier score will be identified as the outlier. So let me give you an example of the commit which has the highest outlier score. If we only look at the number of deletion, and the number of change file, it's quite normal. However, if we look at the date and if we look at the time the commit has been made, which is 3:11 a.m. If you remember the example I just gave you at the beginning of my presentation about the working pattern of the engineer, 3:11 a.m., that's not usual. So what can we tell from the result? We can tell the deep ECOD shows the potential can identify the unusual commit from the unlabeled real-world data, especially when the data set is unimodal distribution. So from the result, we can draw those 2 conclusions. First, our proposed method, deep ECOD, outperforms 8 other anomaly detection methods on 9 benchmark data sets across different fields. Especially, we outperform ECOD, which is the second best one. And secondly, deep ECOD is interpretable, which means there's no black box. And also, we don't require any distance calculation. And we made those 3 contributions from our project. Firstly, we propose this novel anomaly detection method, which is called deep ECOD, It not only can detect the outliers from the unimodal distribution, and also can detect the outliers from the multimodal distribution. And secondly, we evaluated our results on 9 different benchmark data set, and we achieved the best performance. And finally, we further evaluated our model on the real-world data set, and we showed it's suitable to the information security. So same as any other research, we also have limitations. So this limitation actually is inherited from ECOD. So we do not consider the relationship between the dimensions. So which means we treat each dimension independently. So which lead to the future work of our project. Firstly, we think we would like to investigate the dependency of each dimension. And also we think that would be very interesting to consider more diverse distribution, because at the moment we only focus on the normal distribution. So thank you so much.
Okay, thank you, Kaixi. All right, we're going to open it up for questions. Oh, there's one right here.
Kaixi, thanks for your talk. As I recall, LODA uses projections of high-dimensional data sets to do unimodal things. Have you considered, speaking of more general distributions, sort of combining what you're doing with LODA to do, projections over higher dimensional things and work with mixtures that way?
Sorry, just would like to double check. Do you mean if I would like to consider LODA as my further work?
No, it seems like there's a way to synthesize what you're doing with LODA, where you've got some high-dimensional distribution and you project it onto one dimension, do the sort of mixture decomposition on the one-dimensional thing and find anomalies that way.
Oh, wow, that's something I never considered, but thanks for bringing it up. I think I would like to investigate it in the future. Thank you so much.
So another question I was wondering about is, you gave the motivating example of, like the GitHub commits. From your experience in the cybersecurity domain, like what are other examples where you've seen anomaly detection potentially fail because of the shortcomings of like assuming unimodal distributions or using anomaly detection methods that don't perform well on multimodal?
In cybersecurity, so I think our main focus is on the commit at the moment. Like especially the time and the date. But we also think, let's say, the tags, that could be one. Another thing we would like to investigate, that's actually our future work, which we are doing now. Thank you.
Yeah, I have a question concerning your proposed model here. So is it only going to detect the unusual events in the committed code, or it also has the potential to detect vulnerabilities in the committed code?
Yeah, thank you for your question. So do you mean vulnerabilities inside of the source code?
Yes, in the committed code, or only the unusual event?
Yes, yeah. So thanks for your question. So actually, that's what we are doing now. So because as you see at the moment, we only investigate the like the time and the numbers, which is metadata of the commit. And then after we identify those unusual commit, we look into the actual source code itself to see it has any vulnerability, let's say, or CVE or CWE.
Oh, okay. You are still working on that, right?
Yes. Yeah.
Thank you.
Thank you.
Okay. We have one question from the Slack, and then there's one up here afterwards, I think. So Emil on the Slack is asking for the AUC evaluation metrics you presented. Was this the AUC average calculated across all repos, or was it averaging across the per repo AUC?
That's average repos.
Across all repos?
Yeah, all repos.
Okay,
yes.
Thanks.
Yeah, so I have 2 questions. One is, how much data do you aggregate? I mean, in the sense that like the example that you gave with people working hours of an engineer. Now, people in different locations may have different working hours. So are you aggregating the entire data set, or are you conditioning it on, say, a location? And and similarly, you could condition on multiple other things as well. So that's one. The other is, what about non-numeric data? I think you're looking at normal distributions that's only pertinent to numeric data, right? So have you thought about non-numeric data?
Thank you for your question. That's a very two good questions. So let me answer the first one. So the first, yes, we actually had a discussion if, what if, let's say, the employees work in the West Coast and someone working in UK, we actually convert that time to the same time. So we consider the time difference so that we can so we can follow the same working patterns. And for the second one, like the non-numerical one, let's say the text, we use like embeddings to one hot encoder to convert it to the numerical data, and then we use the other models to investigate if there is a risk or not risk. Thank you.
All right, thanks, Kaixi.